All right, Physics 106 is chapter 20. We finished waves. Now we're going to completely shift gears. Now we're going to electricity. So we'll do electricity and magnetism. And this is incredibly important if you want to become a doctor. We'll learn later on, we'll do circuits, and the same concepts that we use to describe electrical circuits, you use to describe how blood goes through the arteries and veins and through the different organs. So this is incredibly important, electricity and magnetism for medicine and for most branches of science. Okay, chapter 20, this is the easy chapter. Electric fields and forces. So we want to understand the charge model. Most of you already know it, and use it to explain basic electric phenomena. We'll develop an atomic level understanding of the charge model. Most of you already know that. We'll use Coulomb's law to calculate the electric force between charges. We'll determine the electric fields from charge distributions. And this sounds like 105, doesn't it? Calculate forces and torques on charges in electric fields. All right, so let's just review some things that I'm sure you already know. So as far as electricity, there's two kinds of charges. There's plus and there's minus. And if you have like charges, they repel. So you have two pluses, they repel. Two minuses, they repel. But if you have unlike charges, let me draw it like this. Unlike charges, they attract. All right. A conductor, like a wire, a conductor charges flow along a wire. An insulator, like a dry piece of wood, the charges don't flow. So here's a question for you. So read it and then pause your video and figure it out. Okay, consider two objects, A and B. Object A is charged, object B is not charged. Can you tell whether or not each object is a conductor or an insulator? No! You can't, all right? Both insulators and conductors can be charged. You know, like if you have an insulator like a plastic rod, you can charge it by rubbing it or by touching it with something that's charged. For a conductor, you can charge it by touching something that's charged. So insulators and conductors can both be charged. The only difference between an insulator and a conductor, as I said a minute ago, for a conductor, charges flow. For an insulator, charges don't flow. I mean, you can think of an insulator as a crummy conductor, if you wish. All right, so let's learn something else, which is kind of interesting. So here we have a metal ball, and it's uncharged, so it's neutral. And this is an insulating string or wire or something like that. Think of a string, insulating string is hanging from the ceiling. All right, whoopee. So then what we do, we bring this charged rod close to this neutral metal ball. No touching though, okay? No touching. Just bring it close. So the question is, what happens? So pause your video and come up with an answer. Okay, now remember, this is neutral. This is charged. So you may think number 3, but you'd be wrong, all right? So what actually happens is that this metal ball is attracted to this. Now you say, well, how can that be? This is neutral. Well, that's what we want to discuss. Oh yeah, okay, so first you have to answer this question, all right? Okay, so come up with a reason. So pause your video and figure it out. All right, here is the answer. None of the above, all right? Charges do not move back and forth between the rod and the ball. I mean, they don't move across a large region of air. We don't know anything about magnetism, so that's ridiculous. And let's see, and this is ridiculous as well, all right? Neutral is neutral, okay? Neutral and negative they're not opposite charges, and this is just wrong, all right? So none of the above. So let's see what's going on. So there's really two cases we have to talk about. We're going to talk about a neutral conductor and then a neutral insulator. All right, so this is supposed to be like the neutral metal ball, and this is the charged rod. So this is what happens. So again, this is neutral, right, but it's metal. So that means that charges can flow. It's a conductor. So when you approach this neutral metal with something that's charged, well, what happens? You know, the electrons can flow in a conductor. So what happens? So these electrons, they're attracted to these positive charges, so they flow to the right. Well, if the electrons flow to the right, that means there's positives left, you know, on the right. I mean, did I say that right? Electrons flow to the left, leaving positives to the right. Okay, so let's read this. All right, so the sea of electrons in the metal is attracted to the positive rod, and it shifts. It moves to the left, so that there's an excess negative charge on the near surface. A deficit of electrons, a net positive charge, is created or left behind on the far surface. But you know, this thing is still neutral. The metal's net charge is still 0. But it's been polarized. That's the key word here, right? So when the electrons move to the left, or the sea of electrons move to the left, leaving a bunch of positives on the right, we say that this metal has been polarized. Okay, so what happens? If this is positive, and you have this negative over to the right, they're going to attract. Agree? They're going to attract. All right, so that was with a conductor. Oh, by the way, this is kind of interesting. You know, this picture is totally misleading. So, I mean, it kind of implies that the entire sea of electron moves from here to here, right? It's total garbage. The sea of electrons, it only moves about 10 to the minus 15 meters. I mean, that's incredible, right? I mean, it hardly moves at all. 10 to the minus 15 meters, that's nothing. But it moves a little bit, right? And just that little bit is enough to cause this, you know, these to be attracted. Okay, so that's a conductor where the sea of electrons actually moves. All right, and again, we call the metal polarized. Well, how about an insulator? I mean, with an insulator, you know, the sea of electrons doesn't move, right? It's an insulator. That's an insulator. The electrons don't move. But here's what happens. So the insulator is made up of atoms or molecules, and here's an example. Well, this is water, right? But I just want to give you an example of a polarized atom. So this is H2O, right? And if you take chemistry, you'll learn why this is 105 degrees, but we don't care right now. But the point is, here's a positive nucleus, here's a positive nucleus, here's a positive nucleus. So wouldn't you say that this part is more positive than this part? Well, yeah. Okay? So we say that water is a polarized atom. So we model it like this. This is just a model, a simple model. We model it like this. And we'll talk a whole lot more about this later on. So we say like there's a positive part and a negative part. Well, you know, a lot of molecules or atoms in the real world are polarized. In other words, we can model them like this. Okay, so just think about it. Before this charge was here, you know, these things are just randomly oriented, just random, right? But then when you put a plus charge here, what are these polarized atoms going to do? Well, they're going to rotate ever so slightly so the negative is attracted to this and the positive is repelled. Okay? So that's basically what's going to happen. The atoms are just going to rotate. Well, what do you notice now? You notice that this side is slightly more negative than this side. So therefore, what is this insulator going to do? This insulator is going to be attracted to this external charge. So that's also called polarization. So there you go. All right. So I mean, so it's kind of interesting, right? So what we're saying, I mean, go back to this. You got to understand this. What we're saying is that a neutral object, right? Either a metal, either a conductor or an insulator, is going to be attracted to a charged object. But you've got to be careful, though. This has to be large. Well, what do you mean by large? I mean, like, if this were a neutron, I mean, it wouldn't work, right? Because you can't polarize a neutron. I mean, a neutron is a neutron. So, I mean, it has to be kind of big. It has to be able to be polarized, all right? So just remember that. A large neutral object, either an insulator or a conductor, is attracted to a charged object. All right, now let's see if you can put this to practice. All right, so 3 pith balls are suspended from thin threads. Pith balls are just little balls that have a conducting surface. Various objects are then rubbed against other objects, nylon against silk, glass against polyester, etc. And some of the pith balls are charged by touching them with one of these objects. It is found that pith balls 1 and 2 attract each other, that pith balls 2 and 3 repel each other. From this, we can conclude that, all right, now, so what I suggest you do, I mean, it's the only way I can think of it, is make a table. So make a table. So just make a table and just have, different rows and just figure out the possible charge combinations, right? So pause your video and figure this out. This is a good test question, so you don't want to memorize it. You want to be able to figure it out. All right, let's go over it. Okay, so it says that 1 and 2, 1 attracts 2. All right, so 1 and 2 attract, and then 2 and 3 repel. So 2 and 3 repel. Okay, so let's just do the different possibilities, So if 1 and 2 attract, well, that could be negative, that could be positive, right? And, but if 2 and 3 repel, that means 2 has to be the same thing as 3. Okay, so that's one possibility. Let's do another possibility. Let's say, okay, let's have that plus, that minus, right? Because 1 and 2 attract, but since 2 and 3 repel, that has to be the same as that. All right, that's fine. But wait a second. These are large objects, right? They're not neutrons. So this could actually be neutral, right? 1 could be neutral and be attracted to 2. But 2 and 3 repel, so that's that. Or we could do it the other way, right? 0 minus minus. All right, so what can we say? I mean, what's the answer? There's all sorts of different possibilities, right? We can't answer the question, all right? We need to do more experiments, right? Let's look at it. I mean, 1 and 3 carry opposite charge. Well, not necessarily, because that can be neutral, right? So 1's wrong. 1 and 3 carry charges of equal sign? No. All 3 carry the charges of the same sign? No. One of the charges carries no charge? Well, maybe, but not necessarily. All right, so it has to be 5. All right, now we're just going to talk more about the charge model. We're just going to talk about the various characteristics of a charge model. Okay, so charge is quantized. Okay, so little e is the charge of an electron. It's also the charge of a proton. If it's negative, electrons have negative charge. If it's positive, it's the charge of the proton. So this little e is the charge of the electron or the proton, magnitude. So if you ever measure anything in nature, the charge, little q, will always be some integer times e. And that's what it means to be quantized. You'll never measure the charge of anything in nature that has a charge of like 1.5 e. It just doesn't work that way. It's kind of like going to Foodland and say, I want 1.5 eggs. You can't buy 1.5 eggs, right? Eggs are quantized. They don't come in units of 1, or 2 or 3. I mean, there's like an integer, And so charge is quantized, plus or minus an integer times the charge of an electron. Okay, something else that we know about charge, it's conserved. What does it mean to be conserved? Well, you know what it means to be conserved. We learned that in 105. It means that, the total charge before some process or interaction equals the total charge after some process or interaction. So let's see if it's true. Okay, so here's the before. It's a neutron, so it has 0 charge. So that means everything after has to have 0 charge. Well, let's see. That's an electron, charge -1. That's a proton, charge +1. That's an antineutrino, no charge. So -1 + 1, 0 equals 0, right? So the total charge before is 0. The total charge after is 0, because charge is conserved. It never changes. Let's do this. So you smash an electron with a positron. What's the total charge here? 0. So what does the total charge have to be here? 0. So 2 gamma rays. They don't have any charge. Here you can have a gamma ray decay. The charge before is 0. What's the charge after? 0. So that's what it means that charge is conserved. Charge is always conserved. Okay, so this is what we've learned so far. 2 kinds of charge, plus and minus. Like charges repel, unlike charges attract. Large, and of course I put quotes around the large because I mean it's like, what's large, you know? Like bigger than a molecule or something. So large neutral objects are attracted to charged objects. And charge is quantized, and charge is conserved. Okay. Now, we've talked about this, like charges repel, unlike charges attract. Well, that's fine, but we'd like to know, the strength of the forces, right? We want to know the magnitude of the forces, okay? Because we already know the directions, right? We know the directions, but we want to know the magnitude. So this is this is called Coulomb's law. So Q1 is the charge of this object. Q2 is the charge of that object. This is the distance between their centers, d. So the electric force equals K. I'll get to that. The magnitude of Q1, the magnitude of Q2 times the distance squared. Now, where have we seen an equation like this before? A constant times something divided by distance squared. That's gravity, right? We've seen, the law of gravity had that same form, right? The same form. All right, now what's this K? Let's talk about K. All right, K is a constant. You'll see it all the time in electricity. So, all right, so K, I'm sorry to do this to you, but K is 1 over 4 pi epsilon 0. Why would you do that? You'll see later on. So K is a constant, epsilon 0 is a constant. So for now, we're just going to call it K. And, all right, K is actually 8.99 times 10 to the 9th Newton meter squared per Coulomb squared. That's the uppercase C. But as far as we're concerned, we're just going to call it 9 times 10 to the 9th. So it's kind of easy to remember, right? 9 times 10 to the 9. Okay? So for a while, we're just going to call it K. And then later on, when we start having pi's everywhere, we're going to actually say K is equal to 1 over 4 pi epsilon 0. So you'll see. Don't worry about it. It will all make sense. All right. Now, from your experience, which force is the greater force? And I just talking about household objects. So I don't consider the Earth a household object, right? Just household objects. Which force is greater, gravity or electricity? Just think about it. Think of your experiences with household objects. Which force is greater? Think of, well, I don't want to give it away. Just think of your experience. Well, here, think about this. So here's a balloon. So if you take a balloon, rub your hair with it and stick it on the wall, it will attract, right? That's one of these polarization things. So you have a charged balloon attracted to a neutral wall. Now think about it. The entire Earth is pulling down on this balloon, right? But yet the electrical force is strong enough that it just stays there. Okay, it remains attached. So what do you say? The electrical force is gobs and gobs stronger than the gravitational force for household objects. Think of another thing. You don't really see this a lot in Hawaii, but like if you live in a dry climate and and you're grabbing your clothes from the clothes dryer after it's dry, you know, sometimes it sticks to you, right? That static cling. So think about it. The whole earth is pulling down on your shirt, let's say, but it's sticking to you, you know? And so electrical forces are much, much larger than gravitational forces. Now, so here's a nice example. I really like this example. So here's a hydrogen atom. You know, a proton, a plus charge, an electron with a negative charge, you know. They have masses, right? And so there's a gravitational attraction between them. And so we can just use what we learned in Physics 105, and we can figure out, we can use Newton's law of gravity and figure out the, you know, the gravitational force. Or we can use what we've just learned now, we can figure out the electrical force using Coulomb's law. Now you can kind of see which is going to, well, notice that this is 9 times 10 to the positive 9, 6.67 times 10 minus 11. Anyway, if you plug in the charges in the distance or the masses in the distance, the electrical force is more than 10 to the 39 times the gravitational force. Now, what does that say? I mean, the gravitational force for hydrogen is nothing. Come on, 10 to the 39. What would you do with 10 to the $39, huh? Or even cents, but anyway. All right, now, remember, Coulomb's law gives you the magnitude of the electric force, and then we know the directions just by, you know, like charges repel, unlike charges attract. So this electrical force is a vector, right? The electric force is a vector. And if it's a vector, that means that the total, you know, the total electric force is just the sum of the individual ones. I mean, no kidding, right? That's Physics 105, right? So that's not a big deal. All right, this is actually a Physics 105 question, believe it or not. So 2 uniformly charged spheres are firmly fastened to and electrically insulated from frictionless pucks on an air table, no friction. The charge on sphere 2 is 3 times the charge on sphere 1. Which force diagram correctly shows the magnitude and the direction of the electrostatic forces? So pause your video and figure it out. All right, so what's the answer? Why? Because Newton's third law, right? F1 on 2 equals F2 on 1. Magnitude, right? Magnitude. If you want to do the directions, you're going to do that. Right? I don't care if one has 3 times as more charge on the other one. Newton's third law still holds, right? So there you go. So don't forget Newton's third law. Okay, so we're going to be doing, you know, force diagram type problems with electricity, just like we did in Physics 105. And you're going to be giving a diagram of all these different charges, and then the question will say, you know, what is the net force on one particular charge? It's just like 105, right? You know, you had all these different forces acting on an object, and you had to figure out the net force on one particular object. Well, in Physics 105, what did you do? You drew the force diagram, you know. You drew the force diagram, and you drew the object. And then you drew all the forces acting on the object, like, I don't know, maybe, you know, tension or whatever, friction or, you know, gravity, normal or whatever, you know, but you only draw the object. Then you just draw the, you know. So it's the same thing. Nothing's new. So here's an example. All right, here's an example. The figure below shows an arrangement of 6 fixed charged particles, where this distance A is 2 centimeters and theta is a nice 30 degrees. All 6 particles have the same magnitude of charge. Q equals 3 microcoulombs. Their electrical signs are as indicated. What is the net electrostatic force F acting on Q1 due to the other charges? All right, so what are we going to do? We're going to draw Q1. I mean, that's what we always do, right? Okay, so there you go. You draw Q1. All right, now we're going to be super lazy. I mean, you know, if this is, what would we do in Physics 105? You would say, you know, the sum of the x forces equals blah, 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 and the sum of the y forces equals blah, 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 right? Well, we're going to do that, but we're going to kind of be lazy. Or smart. All right? Smart. Okay, so this is the object. So we want to see what all these forces do to the object. So it doesn't matter the order, right? Okay, and don't forget, Coulomb's law, F just equals K, Q1, Q2 over the distance squared. But here all the Q's are the same, right? So it's going to be K, Q squared over distance squared. Okay, so let's do what do you want to do? Let's do the force that this guy exerts on that guy. All right? Well, they're both negative, so it's going to be what's going to be the direction? That way, right? Because like signs, like charges repel. Okay, so it's going to be that way. Now look, here we have the charges that are 2A, A, 2A apart, right? And the Coulomb's law is this over the distance squared. So, right? So this one is always going to be a fourth of this one, and that one, and that one, right? Because this is 2A, and that's A, and it's the distance squared, right? Right? All right, so this force is always going to be a fourth as much as that fourth. Okay, so the force that this guy exerts on that guy, it repels, it's a fourth as much as these guys, so it's going to be that way, kind of small. Okay, so there's the force that 2 exerts on 1. I would have wrote it 2, 1, but whatever. All right, let's do this one. Let's do the force that 3 exerts on 1. Now you notice these are opposite. So what is 3 doing to 1? It's pulling it up here, right? And notice it's only A apart. So that means that this force is going to be 4 times as much as this force. Because again, this has a d squared in the denominator. So that means that this negative charge is going to go this way 4 times that. So, something like that. So, rotten picture. All right, so there it is. All right, so there's that. Now, we don't like these, do we? What do you always do with a vector that's not along the coordinate axis? You've got to resolve it into components, right? Physics 105, all right? So here's, call it F13, so there's cosine because it's adjacent, and there's sine opposite. All right, now let's do all the other ones, all right? So, so this one pushes it to the right. This one pulls it to the right with a large force because it's only A. So there's F16. Okay, what is this? What does Q4 do? It pushes it that way with a small force because it's 2A apart. So there's F14. What does Q5 do? It pushes it down this way, pushes it down that way. And again, they have the same charge, right? They have the same charge. So the magnitude of this force is going to be the same as the magnitude of that force. So that one gets pulled up. This one gets pushed down. You resolve this. Okay? So I think we've done them all, right? Have we done them all? Yeah, we've done them all. Now look, life is good. This cancels that. This cancels that. This adds to that. Now it says sine of 30. What's sine of 30? It's a half. So that means that this is going to be half of this. This is going to be half of that. But remember, this is equal to this. Yeah? All right, so this is half of that. This is half of that. So if you add that to that, it exactly equals that, but the opposite direction. So what's the net result? Our famous our favorite number, 0. All right? So what's the story here? What's the moral of the story? We could have done that, and it would have been fine. But, sometimes you can just kind of look at it and just draw everything out, and you don't have to write a thing down, and you can actually solve it, Just draw your vectors and just resolve all your vectors, and you have to know what sine of 30 is, I guess, and you can just figure it out. If you don't feel comfortable doing that, just do that. Not a problem. You're going to get the right answer. All right, good place to stop.